potential syntheses that we can create through these roadmaps. For class handout number 1, the first reaction that we see, reaction 15A, is how to make a organometallic from an alkyl halide. All right, let me start with an alkyl halide. Everyone's roadmap will be a little bit different. Do I want that one? Give me 1 second. Okay, let me do this one. All right, reaction 15A. Let's make the reagents a different color. And I chose magnesium. The product, again, another different color. Okay. In notes, let's see. We don't need to know the mechanism for this, but I'm going to put here a little note. Use aprotic. And so an example of an aprotic solvent is ether, diethyl ether. And the other one is, other note is also, you could make an organolithium. Okay. Before we move on to our next reaction in the handout, maybe we could learn also how to make alkyl halides, recalling reactions from last semester. And that's why I was struggling a little bit with the alkyl bromide, because I wanted to make sure that we could make this. Oh boy. Let's make this from a alkene, and that'll be HBr. And so the alkene that would give us this product is that. We'd also use an alcohol, right? This was, again, the general rule is if you see it in the ACE answers, you are responsible for it. Remember the alcohol version, you could use HBr or PBr3 or HBr. That comes from an alcohol. Oh, whoa. Yep, that would give the same Roman. Okay, let's move on. Again, anytime we use a Grignard, which is, as you know, this magnesium organometallic, we could also use organolithium. And the first reaction that we saw with the organometallics is epoxide. Let's make this arrow a little bit bigger. And, oops, nope, that's wrong also. I have to come from the Grignard. Okay, the epoxide, let's make it asymmetrical. And what did I use for acid? H3O plus or H2O, HCl. Okay. Now we have to go change colors. So the Grignard is green now. Let's use purple. The dots here. I would copy the Grignard first. Make it bond to the dot. That dot has a carbon, another methyl, and off of this carbon is the OH. You attack the less substituted carbon, and in red, I'm going to put here a M in parentheses, because you need to know the mechanism for this reaction. Oh, also, it's up to your preference. How much material do you want to put on a roadmap? you don't want to put every single detail because it kind of defeats the purpose of a study aid, right? The study aid is trying to condense, show you the most important points, so it's very easy to study and memorize. But here, I do want to make a point that you may need to know stereochemistry as well. We don't have any stereochemistry on the roadmap typically because I want to condense everything and simplify it. But if you had wedges and dashes on the epoxide, right, you would have backside attack. I think the most important part here is that you got to know the mechanism. Okay, and if any of this is unfamiliar, well, we're doing this in order. So this is from class 1 handout. Okay, we do have one other reaction in the class 1 handout, and that is if you accidentally destroy your Grignard with water or some protic molecule, and it could be any protic molecule. It could be water or alcohol or amine, something with a hydrogen on a oxygen or nitrogen that's easily, given up. It's you're reacting it with an acid. Okay. Well, what happens here is that let me put this in green to emphasize where that hydrogen is. It's literally in orange, that one. Okay, so the Grignard is basic. It picks up an acidic proton. You know the mechanism for this. A lot of these, I don't even have to put the M. It's just, oh yeah, you know that this Grignard is grabby. It either attacks a carbon or takes a proton. So you know the mechanism for that. Okay. I believe that's it. I do see an example in the class 1 handout where it's impossible to make a Grignard reagent because it's self-reactive. But I'm not going to put that here. Again, we are trying to, condense and get the most important points. Now, class 2 was the handout for HOMO and LUMO. So there isn't any new reactions here. In class 2, we were explaining why there was backside attack and how to break a bond by populating the LUMO, the antibonding orbital. So we're done with class 2. Let's move on to class 3, where we start looking at aldehydes and ketones. And the first one is with formaldehyde, the Grignard with formaldehyde. I am going to run out of space, but I can fit in one more arrow here. And formaldehyde is a specific molecule, the simplest aldehyde. And let me use it just H3O+. We're using purple. Why did I choose this organometallic? Why did I make it so complicated? So there, make a bond to the dot, and you make a primary alcohol. Okay. Well, I am running out of space. So I know we have other Grignard reactions. Let me write another Grignard city right here in the middle. Let's do something. Let's emphasize that your carbon metal bond could also be between a metal and a carbon sp2. Okay, I'll stick with the Grignard, but let's do something like that. Practice other carbon skeletons. Okay. Oh, mechanism. Don't forget that. M here. Okay, orange. Next, a normal aldehyde or I don't want to say normal, but an aldehyde that only has one hydrogen on the carbon. Okay, that's fine. Let's do this one. Let's practice. Let's put a CHO. Okay, you know CHO? And 2 H3O+ again. Let's go this way. You're always free to pause the video. Yeah, let me do that actually. Let me give you some more reactions and you fill in the products. The next one I see is with a ketone. Let me give us a cyclic ketone. Okay. All of these you'll need to know the mechanism, the ones with the organometallic. Okay. Try to fit in that product. You could pause the video. Next one is, I'm just looking at class 3. This is something that you can do as well. On page 3, I see carbon dioxide. And let me just go back to HCl, H2O. And again, it's mechanism. The rest of class 3 is, if I gave you an alcohol, can you predict the type of organometallic and carbonyl group or compound that you need to use? I'm looking more. Oh, I have also in class 3 a couple more thoughts about the MO. This time of a CO double bond. Oh, page 5. We take a look at some practice. You know, we're practicing with the TRO group. What? How about making this aldehyde? Yeah, this is from Organic 1. I don't have a lot of space here, actually. I would still like to put it though. How about this one? Let's draw an arrow. How do I do the review stuff? Let's put an arrow from here to that TRO. How do you make that aldehyde? From what can you make it from? Well, you can make it from a alcohol, and it will be a primary alcohol. Okay. Do you remember the reagent for this? This is PCC. You don't want to... I'm just checking my carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You don't want to over-oxidize to the carboxylic acid. So we're going to use... What color? We're going to use PCC. Okay. Obviously, again, the roadmap is to your liking, to your style. So if you need to rearrange some cities, get it to look a little bit less congested, you could do that. But you see how we took an organic chemistry 1 problem or reaction and made an aldehyde, which in turn we could react with the Grignard. Okay. Pause the video, fill in the products here, here, and here. While I look through the rest of the class 3 handout. Okay. Class 3 is done. We have here, okay, from the organometallic, make a bond to the dot. The dot is now actually this carbon here. And so we have an OH for sure. 1 carbon, another carbon that's branched. If I make a mistake, be the first one to let me know and I'll give you an extra point. Okay, here again, look at the strategy. Make the draw the organometallic, make a bond from it to the dot. Ooh, that dot is now part of a 4-membered ring. So 1, 2, 3, and 4. I think that's good. Carbon dioxide, make a bond to the dot. That's a carboxyl group. Okay. All right, going on to class 4. Okay, class 4, aldehydes and ketones with other carbon nucleophiles. So we are done, it looks like, with the organometallic. So now we're going to have an aldehyde and ketone, and we're going to start reacting it with other nucleophiles. Do I have space? So how do I want to do this? What would be my city? Let's just take a normal ketone. Oh, how about this one, actually? Okay, let's take this benzene ring. You know, in lab you worked with benzophenone. Let's not put another benzene ring on the right. Let's make it methyl. That's called acetophenone. The first reaction in class, we're still in class 4. On class 4 is with the alkenyl anion. Again, orange. How do we want to draw this? Let's draw it like this. Alkenyl anion. So sometimes you'll see it like this. Know that that's can be separated into Na plus C minus, and the minus is going to be attacking the carbonyl carbon. So we'll mark it. I think most of the reactions we'll see with this attack the carbonyl carbon. You go to protonate to get the OH group. Okay, so that's one. The other one is, the other carbon nucleophile is cyanide. And you'll most likely see it as NaCN, understanding that it's Na plus Cn minus. The minus is on the carbon. 2, HCl, H2O. Okay, that was reaction 2. Same deal. I'm going to fill in the roads. You fill in the product. Next is the Wittig. Oh, by the way, M again, M again. And the Wittig also, you need to know the mechanism. It's just one reagent, the Wittig reagent, with the aldehyde or ketone. And so what has just happened here? Let me give you this Wittig reagent. It's a P plus connected to a carbon that's negative. And we got to make sure it has 3 groups on it, 3 bonds. And so let me give us CH3, and let's give us something a little more complicated like that. Okay, carbon with 3 bonds is negative. Oh, 3 bonds in 1 lone pair. You don't have to draw the lone pair unless you use them in the mechanism. So I'll just leave it like this. You do need to know the mechanism. Okay. And that's it for class 4. I did show you how to make the Wittig reagent. Let's fill in the products first, and then how to make the Wittig reagent, which may come up. It's kind of a minor reaction. This is the more important part, right, to use it. And for the first reaction here, we have a dot. That O becomes an OH, and then you got to make a bond. Okay, so the dot to the letter C. I'm not going to draw the letter C, but it's this one right here. And then, so that is a triple bond. Another carbon and another carbon. You can always count carbons. You made a bond right here. So on the left side, you have 7 carbons. On the right side, you have 4. And that's what we expect. For the next one, we have the same deal. The dot has an OH group, and now we have a cyanide group. You could abbreviate CN. Or some people like to draw and remind themselves that that is a triple bond. The Wittig. The Wittig, draw one of them, either the ketone or the Wittig reagent, but I like the ketone. Draw the ketone first. Oh. Did anyone catch that mistake in the previous 2 reactions? See this right here? You can draw it in any direction. Boom. Boom. Okay. Here for the Wittig, okay, there's the methyl. You double bond, and then you're attaching this here. So that C will be this C over here. And so it doesn't matter cis or trans. This is technically, the way I'm drawing it, technically cis. The 2 big groups here are bumping. Okay. Class 4, I did show you how to make the Vidig, and let's see. Let me do it this way. So how do I make that right here? Okay. It came from an alkyl halide. So look at the carbon part. The carbon part looks like this. And then we have here, this was a Br. Okay. I know it has a hydrogen, but we're going to strip it off in the reaction. So the first thing is to react it with PH3P. It does have a lone pair. I like to remind myself of that, but you don't have to draw the lone pair. And 2, once that P attacks, this phosphorus attacks this carbon and kicks out bromine, we got to get rid of this H, because that carbon has no H's, right? And we're going to use a strong base, and I think I use NaH in the handout. Okay, that's class 4. Ready for class 5? Class 5, we're still dealing with aldehydes and ketones, but now we're attacking it with oxygen, which is good because we can still use this ketone right here. And let's make a hydrate. Not a very important reaction. Well, it's an important reaction, but to me it's very boring. Okay, so water. And actually I do want to emphasize that though this happens pretty readily, the equilibrium is still to the carbonyl group. Okay, and we have the hydrate. Don't forget that methyl. Next, you want to do the acetal. The acetal goes through the hemiacetal, but since we're going to use excess alcohol, we're going to push all the way to the acetal. And let's say excess ethanol. Let's practice abbreviations, ETOH. And we're under acidic conditions, H2SO4. Or you could use HCl. How do I do this? Draw the ketone first. Whoops, wrong color. Draw the ketone first. And then you have 2 alkoxy groups. You have this one. So ET is ethyl. 1, 2. 1, 2. Okay. It goes through the hemiacetal, and you'll practice the mechanism. This is one where I do think it's useful to know the number of steps. So 3 steps to the hemiacetal, 4 more steps to the acetal. Okay. Next, we have a kind of offshoot of this is the formation of the hemiacetal, where we stop at the hemiacetal. And we're going to use a molecule that has an alcohol and a carbonyl in the same molecule. And so the classic example, I'm going to have to, I do want to leave it, I do want to keep it on this page. So let's go green again, and let's put the, you'll see why I'm doing it this way, I think. Let's put the aldehyde way down here. 1, 2, 3, 4. Okay. You have to recognize that, okay, there's the carbonyl and we have an OH group. And especially if you have acid, which we're going to put, you're going to start thinking about how is this going to, what's most likely to happen, okay? You're under acid, so you're going to protonate the carbonyl oxygen, and it's going to be very susceptible to attack. Well, what's going to attack the protonated carbonyl? That dude right there, to make a 1, 2, 3, 4, 5-membered ring. I think I accidentally erased that. Okay, 5-membered ring. Whoops, color. 5-member during one of the members is oxygen. We attack the dot, okay, and you know that carbonyl group becomes OH. We don't have excess alcohol in this example, so we're not going to make this part into an acetal. This is where we're going to stop at the stable cyclic hemiacetal. Well, on the dot, I'm looking right here, we have CH2, CH2C, and then on the third C, we have a methyl. CH2, CH2, on the third C, we have a methyl. Okay? That OH becomes an O, the OH that attacked. That is your cyclic hemiacetal, M. Okay? So we have the product of hemiacetal and acetal formation here and here. Okay? Remember, this one went through the hemiacetal, but we don't stop because we have excess alcohol. The last... okay. Now, if I give you... This is going to be something that people are not going to quite be ready for, I think. But if I give you the hemiacetal, a hemiacetal here, and then I add alcohol, more alcohol. For instance, let's do methanol. Okay. Whoops, there shouldn't be a 1 there. Okay, let's do this again. Methanol. Under acidic conditions, let's do HCl. Okay, so this is implying that we're going to take the hemiacetal and we're going to make it the full acetal by adding more alcohol. And thus you have this. Whoops, slow down. Okay, you know this. It's just that you may not, it may not be obvious to you at first. You know why I say this? Because you know that this is an acetal. So how did that happen? You attach 2 alkoxy groups to the carbonyl. The first one is within the molecule. The second one is replacing the OH. Remember how we kicked out OH as water? And so that mechanism you would want to know. This is the 4 steps, right, to the acetal. Okay. I don't have any space, and I do want to show... Oh, I do have space. Let's show hydrolysis, okay? Hydrolysis is pretty easy to recognize because you have acidic water. You go to lyse with water, so H2O, and sometimes instead of HCl I use H2SO4. Right? Dot, cut. And so, I don't know what color to use now. And so what we have is the original carbonyl plus the 2 alcohols. And you don't have to draw both, but I typically do. Okay, the 2 ethanols. You could hydrolyze this as well, this one here. I'll make it very clear whether I want you to hydrolyze it completely, right, to get back to the aldehyde or to the carbonyl and the 2 alcohols, this alcohol and this one. In practice, because cyclic hemiacetals are pretty stable, you actually only hydrolyze 1 group, and you keep the hemiacetal. You only hydrolyze that when you do the, you don't want to get too crowded, but when you do the hydrolysis. You don't need to know the mechanism for hydrolysis, but I did show you tricks on how to get the product right away with this dot and the 2 cuts. All right, so that's good. We're done with class 5, and in 5 class, those are all the reactions in class 1, 2, 3, 4, and 5, the new ones for organic 2. When we start looking at class 6, 7, 8, now we're going to look at carbohydrates and apply these. So I like that. Let's see what we can come up with in terms of getting a a practical roadmap for carbohydrates. So this is continuation. So I'm looking at class 6. In class 6, I backtracked a little bit to talk about, why do we protonate the carbonyl group to make it more electrophilic? Why do we only favor 5 and 6 membered rings? Because of angle strain. So there's nothing new in class 6 in terms of the reactions. Class 7, we do have the application of, we do have the application of hemiacetal and acetal formation in class 7 and 8. So let us draw a random monosaccharide and let's practice. Let's practice with the harder ketose. And so let's do CH2OH. CH2OH. The double bond oxygen for ketose will always be carbon number 2. And randomly, OH, OH, OH. We're going to perform a hemiacetal formation. And so we're going to make this cyclic. We'll do it under acidic conditions. So you've done this before. I have to tell you if I want a 5-membered ring or 6-membered ring, because in many cases both are plausible. Give me 1 second. Okay. Let's make a furanose. Ay. Furan. One more time. Furanose. 5-membered ring. 6-membered rings are called pyranose. Let's make the beta anomer. Okie dokie. If I want to make a 5-membered ring, and we're going to attack this dot, which is carbon number 2, we are going to use this oxygen right here. I think that's 5. Let's count. 1, 2, 3, 4, dot. The convention is, to make things a lot easier, draw your oxygen at the top. Give yourself a bit of space, because what I notice is that this is L, not D. And when it's L, your last carbon number 6, in this case, is going down. And so, I don't like how I drew this. Let me get rid of... Okay. Let me make this a little bit more angled. Drawing something down in the 5-membered ring is pretty easy. It's right here. Okay? And CH2OH. Let me try this again. So that's carbon number 6. Okay, you could label it. This is carbon number 5. Just carbon number 5. Alrighty. So now I took care of the 5-membered ring. I took care of the L. Now I'm going to take care of the beta. And so the beta means cis. So the OH is on the anomeric carbon is cis to that. Okay. Let me do this. Let me take advantage of this paste and copy. So that's my first step. The second step, let's see if this works. Oh yeah, look at that. The second step is to, let's take care of the beta. And so the beta is going to be there. That's carbon number 2. And while we're at this point, why don't we make sure we take care of carbon number 1? So if the OH is going down, carbon number 1 has to be going up. Right? I'm just copying this part. Now these two can switch if I wanted the alpha to this dude here. Okay, that is a good second step. Oh my goodness. Okay, paste the copy again. All right, the next things to take care of are the OHs in the middle. So that is for 3, 4, just 3 and 4. Right? We took care of the OH on 5, which is now this O. Fantastic. So on carbon number 3, when you tip it to the right, that OH is down. And same thing with carbon number 4. And so, again, just to label the steps, we did this first and second, and this is done. Okay? All right, so that takes care of class 7. Okay, I asked you to memorize some things also, some structures. Class 8, there is one more reaction, anomerization. And so we could actually use the cyclic hemiacetal we just made. Is that red? And then so we're going to use HCl under acidic conditions. We're going to do what's called anomerization. You just make the other anomer. So on the anomeric carbon, we have the OH down right here. So to make the anomer, we're just going to make it up. Okay? That's as simple as that. I did give a mechanism. So you could, challenge yourself and draw the mechanism for this. It's hard because there's a lot of, it's a big molecule, right? And you have a lot of groups hanging off the ring. Everything else stays the same. None of the other chiral carbons change in anomerization. M, right? Okay, let me go through class 8 again. Handout, just double check. Oh, I totally forgot. You can make an acetal. And we saw how to make an acetal right here at the very bottom. And so on this page here, we have a bunch of hemiacetals, right? Hemiacetal. So if I choose to make a full acetal, one way to do that is add an alcohol under acidic conditions again. Okay. Remember what happens here? The OH is the only thing that is reactive, not the other OH groups, because, I said it weird. The OH of the hemiacetal is the more reactive of the OH than any other part of the molecule. That's because in the mechanism, you can kick out this OH by using internal lone pair. You can't really kick out these other OHs. And so the product here, instead of an OH down here, you have O-ethyl coming from that group there. Right, we made an acetal. you've seen this before. It's just that you may not recognize it in this context, but you know how to go from a hemiacetal to an acetal. Everything else stays the same. We didn't kick out any of these other OH groups. Okay, and mechanism, yes. Remember, to go from the hemiacetal to the acetal, it's 4 more steps. So there are 4 steps to go from here to here, right? Protonate, kick out, attack, and then deprotonate this H. Those are the 4 steps. Okay, and that's it for reactions. Obviously, you have concepts as well, besides reactions. Concepts like I just saw here in class 8. How do you name the glycosidic linkage? And so definitely in the ACE there's practice, but this is why I suggest that you go through the handouts one last time, a day or 2 days before the exam, just so you pick up, oh yeah, we did learn alpha 1,4. Looking at the very beginning, like class 1, what did we learn? Oh, we looked at partial charges, what an umpalong is, or how to umpalong is a verb. How to do an umpalong is basically polarity inversion. How to do a polarity inversion. All right, so I could go on forever and ever, but this video is going to get too long. Again, our purpose was to make maps of the reactions and to mark which ones we need to know the mechanisms for. That looks pretty good. I'm really getting better at this tablet stuff.